Okay, let's do a brief review on oxidation and reduction because in our next topic, our last one, we're going to be using this in a different application you haven't seen before. So I want to kind of refresh your memory on what's going on here. First thing we're going to take a look at is oxidation numbers. All right, and this is basically assigning a charge to everything within a compound, every element. And you have some rules for this. You can actually look them up online. We went through them in class months ago, but it might be something you need to look up to refresh your memory. There's certain things we always start with. So for example, if you have a particular metal on the periodic table that you look at and say, hey, that's in the +1 column, that's in the +2 column, those patterns still exist. So for example, barium is in the +2 column. Now each barium contributes a charge of +2, and there's only one barium atom in this molecule, so its net charge is going to be +2. It's total. Barium contributes +2, and that's it, because there's only one of them. Now we're going to take a look at oxygen. We know oxygen's always -2. Okay, but how many oxygen atoms are really in this molecule? There's actually 6 of them. Okay, and if each one contributes a charge of -2, that's going to be -12 contributed by oxygen. Okay. Now, this is an ionic compound. It's going to make a neutral charge overall. So overall, the value of everything has to equal 0. So what we have to do is figure out what does nitrogen have to be assigned a number of in order for this to be true. What number do we got to put here that would make this a true statement mathematically? And the only number that's going to make that true is +10. So nitrogen has to contribute a +10 charge for all of this stuff to cancel out and basically make 0. However, there's not just one nitrogen atom. There's 2 of them. Okay? And since there's 2 of those, that means each nitrogen atom must contribute a +5 for its oxidation number. These are what I'm talking about when I say oxidation numbers or oxidation states. Okay? So that's what we're looking for, is the charge on each individual atom. Now, let's take a look at some things that maybe have a different look to them, but it's still the same process. Here's P2O5. I'm going to start with the thing that I know. Oxygen's -2. Okay, that's just something we always start with. And there's 5 of them, so that contributes -10. Well, phosphorus has to be something to cancel out that -10, so phosphorus is going to have to be a +10. However, there's 2 of those, just like we had over here with nitrogen. It just looks different with the parentheses. There's 2 phosphorus, so that means each phosphorus must be a +5. There's my oxidation numbers. Now, let's take a look right here. This is something that isn't neutral at all. So this is the sulfate ion. It has 2 extra electrons. It's taken from somewhere else. Okay, and that means it's not going to equal 0 when we're done. We'll start the same way and say oxygen's -2. There's 4 of those, so oxygen contributes -8. However, we're not going to make this equal to 0. It's going to be equal to whatever the charge on that ion is. Okay, so overall, the charge has to equal -2. I need a number here that's going to make this statement true. What minus 8 gives me -2? And that would have to be a +6. And then I work my way back up and go, hey, there's only 1 sulfur here, so the whole entire thing must be +6. And there's my oxidation numbers. So that should kind of look familiar to you. Now, we did this just kind of out of habit. We'd go through and label the oxidation number on everything within a reaction so we could track the movement of electrons, basically. However, there's something you need to recall. Every element, pure element that's by itself, that is not bonded to with any other different kind of atom, is always going to be 0. Okay, so for example, pure iodine, I2, that's got the same number of electrons you would see on the periodic table, same as its protons. It's going to be neutral overall. It hasn't traded electrons with anything yet, hasn't accepted or given any away. So every pure element that's by itself is 0. Iodine is going to be neutral. Over here, chlorine's by itself. It's not combined with anything else other than another chlorine atom, which is identical, so it's going to be 0. Now I'm going to go through and label the oxidation number on each one of these individual atoms. Potassium's a +1, chlorine's a -1. Potassium's +1, iodine's a -1. Okay. What I notice is potassium doesn't do anything. Okay, it stays +1 and +1. I'm not going to really pay attention to it. We call that a spectator ion. It has a purpose, but it's not involved in the transfer of electrons during the chemical reaction. What I am going to do is identify the things that are changing. Chlorine started at -1 and it went up to 0. So it actually got more positive. This is our oxidized element. Iodine started at 0 and went down to -1. It got more negative, This is our reduced element. To me, that's the easiest one to recognize because if a charge gets more negative, it's going down, it's being reduced. However, there's lots of ways to recognize this. Some of you will remember Leo the lion says Gur. That means losing electrons is oxidation, gaining electrons is reduction. Or the phrase oil rig, oxidation is losing, reduction is gaining. Whatever works for you, we have to be able to identify what's oxidized and what's reduced within a reaction. And sometimes you write the entire reaction and nothing gets oxidized and nothing gets reduced. And that doesn't mean the reaction doesn't occur. It just means there's no transfer of electrons within the reaction. Okay, it's a different kind of reaction. So you can have one that actually does happen, but if everything stays the same all the way across and nothing goes up or down, that means we would put no redox. Okay, there is no transfer of electrons. That reaction would not be good for making a battery, which kind of where we're headed with this next week. Okay, so in your next assignment, you're going to be just kind of practicing writing oxidation numbers and identifying what's oxidized and reduced within reactions in preparation for a new application the following time.